Hello everyone. Welcome back to the sessions on DBMS. So today we are going to discuss about attribute closure. Now, given a relation R with set of attributes and a set of functional dependencies, what do you mean by closure of an attribute? It is a set of all those attributes which can be functionally determined from it using given functional dependencies. We have a set of functional dependencies. Using them, how many attributes you can functionally determine through this particular attribute or set of attributes defines your closure. Now, what is the purpose of this? The closure can always help you to identify through which particular set of attributes you will be able to, or otherwise how many attributes you can functionally determine from this, and in that particular scene, if you proceed further, if a particular set of attributes is able to determine each and every attribute of the set, then you call it as a super key or candidate key. So it will help you to identify super key and candidate key. What is the purpose of that? You will be able to reduce this, look at this, you will be able to minimize the redundant attribute and dependencies. It will also help you in normalizing the database, ensuring data integrity, so that the bigger table can be split into smaller tables using this particular candidate key concept. Now, how do I calculate or how do I find or work out on finding closure of an attribute? You start with an attribute set X, that is a set of attributes. The attribute candidate key, you know that it need not be a single attribute, it can be a combination of attribute. So whenever I say it's a key, it can be a combination of attribute. Now assume if you want to find the attribute closure of a set of attributes X, you are trying to find out X plus, I will start with adding all the elements in X into your X plus. Why this? Because your reflexive rule, you know Armstrong's axiom says that X will be able to functionally determine X itself. So that's why I add all those things attributes to X plus. Now for each functional dependency, Y determines Z. If Y is a subset of X plus, then automatically you know that Z can be determined through that. So add Z also to X plus. So repeat this process until no more attributes can be added to X plus. Let's try to see it with an example. Here, given a relation R with a set of attributes A, B, C, D, E and the set of functional dependencies F, which says A determines B, A determines C and C determines D. Now let me try to calculate closure of A. That means initially in A plus you will add A, because we said as per the reflexive rule A determines itself, so I add A. Next, take up a functional dependency A determines B here. Now because A determines B and A is a part of your A plus, I can include B also. We said in our step, when Y determines Z and Y is a subset of X plus, I need to add Z also to that. So from using A, I will be able to determine AB. Next, take the next functional dependency A determines C. Now because of this, because A is a subset of A plus, C also can be added. The next functional dependency is C determines D. Look at this. Because of this, C determines D and C is a part of your A plus, I can include D also into it. Do I have any more functional dependencies through which I can determine? No, I don't have. That means this is the attribute closure of A, B, C, D. Now as per my relation, I realize that A will not be able to determine every attribute of the relation. A will be able to identify or determine only A, B, C, D. So I come to a conclusion that it's not a super key or a candidate key, but let me first give you a definition of super key and candidate key once again. Already we have seen this, but let me just tell you once again. A super key is a set of attributes which can uniquely identify a tuple in relation. That means each and every tuple in the given relation should be able to be identified using that key. Now, for example, in our student database, we say student roll number is a super key or a candidate key or a primary key, which means using that roll number, you will be able to, using the roll number field, you will be able to identify each and every student of the college, the list, whole list, right? So, such a key which will be able to determine each tuple uniquely without any ambiguity is called as a super key, okay? Now, what are the things, characteristics of that? Once you determine that it's a super key, you can add extra attributes, extraneous attributes, still it remains a super key. Because a set of attributes is able to identify, you add extra to that, it doesn't make any difference. That also can be called as a super key. So, each relation can have multiple super keys, okay, many super keys in a relation. Now, look at this example itself. Student ID, email and name are the attributes of a student table. You know, every student will have a unique email ID and every student will have a student ID. So, these two fields can be able to uniquely identify each and every record of your, this is as per my functional dependency, because my functional dependency says student ID can determine the email and name. Similarly, email can determine student ID and name, which says that every email ID is going to be unique for each student. So, now in this particular case, if I see, the super key can be student ID, which will be able to see, look at the student ID, if you see, it can determine email, name, student ID itself. That means all the three attributes it is able to determine. So, it becomes a super key. Similarly, email, when you see, you know how to find email plus, that is your closure of the attribute email can be email itself. Then, you know, through this I will be able to identify student ID and name also. That means all three things are included. So, email and student ID are the super keys which will be able to determine all the other attributes. Now, along with this student ID, I can include email. That's also a super key. Along with email, I can include name. It is also a super key. A combination of student ID and email together is also a super key. That is the definition of extraneous attributes here. Okay. Now, remember, start by finding all the attributes that can functionally determine the entire relation. So, all those attributes which can functionally determine every attributes in the relation, you have to find out. Then if you want, you can just add additional keys there, okay, in order to make more attributes or more super keys for that matter. Now, let us try to see what is a candidate key. A candidate key by definition is a minimal set of attributes that can uniquely identify a tuple in a relation. So, putting it simple, I can even say a minimal super key. A candidate key can be a minimal super key. What do you mean by that? Provided a set of attributes which can uniquely determine each and every tuple. That means attribute closure of a set of attributes which can determine all the attributes. You just have to ensure that if I remove one attribute from that, will that set make a super key? If that is the case, then it is not a candidate key. It is a super key, that's all. It's not a candidate key. That means, remember, a proper subset of a candidate key functionally determines all the attributes, then it is not a candidate key. That means no proper subset of a candidate key should be able to determine all the attributes. Okay, each relation can have multiple candidate keys. We know this fact, and one of them will be chosen as the primary key because they are all the keys which have the capability of becoming a primary key. Looking at this example, again the previous example itself, the candidate key will be employee ID and email. I cannot make a combination of employee ID and name. It can be a super key, but if you see a proper subset of that, that is employee ID itself is a super key or otherwise a candidate key. So, that means it cannot become a candidate key. Proper subset should not be a super key again. Okay, that is why only these two things. How to find them? You find the each attribute or a combination of attribute, find the attribute closure of that. If all the attributes in a relation are determined through that, you select it as a candidate key. Then to ensure that it is, it will be treated as a super key. To ensure that it is a candidate key, remove some of the attributes and see whether that set will also become a super key. If that is the case, then it is not a candidate key. Otherwise, it can be treated as a candidate key. Okay, look at this example. You have a relation with attributes A, B, C, D. The functional dependencies are A determines B, B determines C, C determines D. Yeah, I just want to find the closure of A. So when I want to find the closure of A plus, first you know that I'll include A into it. Then through this functional dependency, A determines B, B will get added. Through this functional dependency, B determines C, C gets added. Through this functional what do you see? C determines D, D gets added. Now the closure of A is A, B, C, D, and that is the set of attributes here. That means A is a super key first. Now, do you have a proper set of A? No, it is null because you have only one attribute here. So there is no proper subset. A itself is a super key. A can be a candidate key. Okay? Now, let me take another example wherein we will try to work out and decide whether which is going to be a, or otherwise how to find the attribute closure we'll try to see, or otherwise how to find candidate key we'll try to see again. Look at this relation R with a set of attributes A, B, C, D, E, and the functional dependencies are A determines B and D determines C, only two things. Now before we proceed, we can just try to identify the functional dependencies, I mean the attributes, prime attributes and non-prime attributes, or dependent or independent attributes, that helps you in cutting down on finding your combination of closures. Otherwise what happens, for every key I have to find the attribute closure, every attribute and combination of attributes. To cut short on that, this can help you. Now in this case, if you see the dependent attributes A and D, which are going to determine other attributes, become your prime attributes. A and D, which are going to determine the other attributes, are called as your prime candidates for your candidate key. Okay, being they can be a part of your candidate key. Attributes B and D are functionally dependent on A and D, whereas C, if you see, it is totally independent. That means C cannot be determined by any of the attributes. So C has to be there in your candidate key. Otherwise it cannot make a candidate key. Let's try to work out on this. Now determine the closure for different combinations of the attributes. Now in this particular case, if you see, I will try to find the closure of A. How to find the closure of A? First include A, then try to see, do you have any dependencies through which I can determine other attributes. So I have A determining B, through which I can include B also. I don't have any other functional dependencies which can be determined through A or B. So only these two become the attributes that can be determined. That means closure of A plus is only AB. Because AB is not determining all the attributes, A is not a candidate key. Similarly, I try to find out for D. D can determine DE, so DE is also not a candidate key. I'll try to find a combination of AD. Now why I am saying directly AD? Because you have seen that A and D are the prime attributes, so they can be a part of candidate key. So with the A and with the D alone, I could not find out. So can I find out or determine all the attributes using AD? I'm just trying to see. So here also I find that using AD, I'll only be able to determine A, B, D, E. C is not a part of it. So now I realize that because C is an independent candidate or attribute, let me include that. So with that intention, I have added A, C, D. Now when I see this, due to the, look at this, D determines E. A, C, D anyway, all three things comes. And because of A determines B, B gets included. D determines E, E gets included. So all together, I'm having all the attributes which can be determined through a set of attributes A, C, D. So I see that ACD is a super key because it is capable of identifying all the attributes. Now, I just have to ensure that ACD is also a candidate key. It is a super key, no use, no doubt. But is it a candidate key also? How do I do it? That checking can be done by verifying, that means remove attributes. Just see whether only A can determine, only C can determine, only D can determine. If not, is the combination AC, AD, CD can determine? No, none of them are capable of determining all the attributes. So, no proper set of ACD is capable of determining other attributes, all the other attributes. That is why ACD is a candidate key. Remember. Now, there is one more thing. We said there can be multiple candidate keys. Now, how do I check? Now, if this ACD is your candidate key, then A, C and D are going to be your prime attributes. If you find that in your set of functional dependencies, any of these things are on the right hand side, of your functional dependencies, then these attributes can be replaced with them. So now say for example, there is a functional dependency which says A determines E. Then in that case, A can be replaced with E. So ECD can be a candidate key. That is a conclusion here, because none of the prime attributes are on the right hand side of your FDs. Where are your FDs? These are the set of FDs. ACD, none of them are on the right hand side. So I conclude that ACD is the only candidate key here. Okay, one last example we'll try to see. Here I am just saying I have taken a relation with A, B, C, D, E and set of dependencies AB determines CD, C and D, C determines A and D determines A. Now let's try to work out on this. The step would be find the attribute closures of single attributes A, B, C, D, E. Then go for combination of 2, then go for combination of 3, then go for combination of 4. So you can go with the shortcut methods by identifying the prime attributes and non-prime or let me say dependent and independent attributes. So that way also it will help you to cut down. Initially I will just show you all the possibilities. Okay, see. I am finding the closure of A, closure of B, closure of C, D and E. None of them, see E is only this, D is capable of determining D and A, C is capable of determining C and A, here B, here only A. Now with this what you understand, none of the attributes individually are capable of becoming the candidate keys. Let me go for a combination. Some of them I am just trying. AB, CE, BD and BE. If you see BE, here I have BD plus, BDA, here I have CE plus which is CEA, AB plus which is ABCD. None of them are capable of identifying or functionally determining all the other attributes. So none of them have the eligibility to become the candidate key. Let me proceed further. 3 set CDE, BDB, BCE. None of them are again capable. See here we don't have A, B, C, D. D is not there. Here also we don't have. Okay, here I don't have C. So none of them are capable. Now let me go for the 4 set. Now here I have taken B, D, C, E because I have seen that D, C and E are the part of my prime attribute set or otherwise dependent attributes. So in this case, I am just trying to calculate the closure of B, D, C, E. All this 4 will be automatically get added. Then because of the final, I will just show you here. See, because D determines A. B, D, C, E anyway got added. because of this attribute D determines A, I am also adding A into this. Now A, B, C, D, E, all of them I am able to identify or functionally determine. That's why B, D, C, E becomes your candidate key. So just remember, a candidate key is the one which is capable of deriving all the other attributes in the relation, and no proper subset of that should be able to determine all other attributes. Then it is a candidate key, and candidate key helps you in dividing your table in your normalization, which you will see later. So here, if I have to ask you to find the prime attributes, all the members of the candidate key becomes your prime attributes and non-members become your non-prime attributes. That's why you see prime attributes are B, D, C, E and non-prime attribute is A. Okay. So remember, attribute closure of an attribute, or otherwise finding the closure of an attributes is very, very helpful for you to identify super keys and candidate keys, which can make a lot of difference in normalizing your tables, in reducing the redundancy and all those things which you will learn later. Thank you so much.